Welcome back to another NeetCode slash LeetCode grind video. Was not able to record a video yesterday because of, let's just say, I got busy, but I was able to do NeetCode yesterday. That's why my streak is still there, right? I think the World Cup is taking a lot of space in my mind, but we were able to keep the streak, right? I was also reading about SQLite. Also, I feel like it's important. I feel like it's very important to read about the tools that you use, right? So I thought, why not just learn about SQLite and just like see how the documentation is, right? Because most of the time I'm learning things from other resources that may not know the full extent of stuff. So I think reading from all of this would be much interesting. So we'll have this for another video or even now. But yeah, anyhow, so let's get on with this. I guess what we'll do is we're gonna do a binary search question first because that's how it is. So let's try to do this question, which I'm practicing at the moment. So cool. So okay, so we have search again. We have search in a rotated array. So how do we do this? The first thing is let's try to visualize what's happening over here. So we're given this sorted array, and if we were to make a graph of this, we would see the graph would just go something like this: 6, 5. Just give me 2 minutes. So this is how it normally looks like. Okay. So this is how the normally the sorted array looks like, but if we were to pivot it, like if we were to rotate the array, how would it look like? So it would look something like so yeah, the way we rotated it is we took some points, we took this, let's say one half, this is the left half, in between like switched their places. So we pretty much took two halves of the sorted array and we pretty much like swiped them, and now our graph will look something like 3, 4, 5, 6, 1, 2, right? This is how our graph will look like, and we have been told to solve this in log n time, so there's some form of binary search to be used. First thing we'll do is we'll do L is equal to 0, R is equal to length of nums minus 1. First of all, let's look at the constraints. Yes, so this is fine. So while L is greater than or equal to R, we'll say something like the middle is equal to L plus R, right? Something like that. Let's format this code real quick. Yeah, so this is our middle. The very first thing we can check is if nums middle is equal to our target, then we can just return middle, right? That is one thing, right? So for example, over here this is 0, 1, 2, 3, 4, 5, 2.5, so this is around 2. So we come at 5, and let's say target is 3. So is 5 is equal to 3 not? I guess then we want to figure out whether we are in the left sorted half or in the right sorted half, so that we can make a judgment call on that. So how can we do that? So the first thing we can do is we can do LF, and I'm going to just check if we are in the left sorted half. And how we can check that is, as you can clearly see, if we are in the left sorted half, if we are anywhere over here, right? If we are over here, 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 one thing you can notice is our nums L will be less than or greater than nums middle. It could be equal to, because what if it's over here itself, like the middle is somewhere 3 and 3 is there. So nums L say less than or equal to nums middle. That means when that half else, sorry my bad, what am I doing? We are in the right sorted half, right? So we are somewhere over here. So right now this is, so the moment we know we are in this half, we could do a normal binary search. And I think the number one thing we can say is if nums L less than equal to target less than equal to nums middle, then we know it's somewhere over here, right? So pretty much it's somewhere in this range. That's good, right? Because it could be equal to this, but it's not equal to this because you already checked it. What we can say is we can say r is equal to middle minus 1. So now पहले यहाँ पे था middle, now this becomes r, this becomes this l, and this turns out to be like a binary search. So the moment this is run, it essentially becomes like a binary search because we have found this is the one sorted half. So this becomes pretty much like binary search because this is our small. I think of it like this is our sorted array, and we're just performing binary search on it, right? But if that's not the case, if it's not in that range, then we want to do middle plus 1, right? um and the reason why we do middle plus 1 is now this will be our L, this will be our R, right? Now we check if we're in the right sorted half, what do we want to do, right? So let's just say if we are somewhere over here, we're in this right sorted half, what do we want to check? Like, so we want to check if nums middle, um, nums middle target nums equal nums R. If this is the case, if it's in that range, then we'll say L is equal to middle plus 1. Else we want to say if it's not in this range, right? If we are in the right sorted half, and first thing is you're figuring out which half are we in. We in the right sorted half, and if it's not in the right sorted half, right, this means it's in the right sorted half, like it's here itself. So we do L, then we pretty much, this is pretty much binary search, right? But if it's not there, then we want to go to the right sorted half, right? And so what for that we can do is R is equal to middle minus 1, and this will continue working. And if it doesn't find, just return minus 1. Let's run test case and see if this runs. So it runs, and so pretty much what's happening is the moment we know, so the first thing we want to check is the middle element equal to target? If not, then we want to figure out where are we in the left sorted half or are we in the right sorted half? So if we're in the left sorted half, and if the target is supposedly in between them, this decays into a binary search, right? But if it's not, then this our job would be to shift this so that we get into the other half that we have not checked yet, right? And so if I submit this, we get yeah, we get that correct. And I think if we submit this again, this might go ahead. So yeah, and I think the yeah, limited rate limiting sequence, which kind of sucks. um so that is essentially the solution for searching in a like a rotated array. The real thing that we really want to work on is finding the minimum in an rotated sorted array. And I was thinking if we could use the same idea. I'll just remove all of this. Right, this is the same thing. Yeah, we're gonna do something like right. So the first thing is we can always do middle. Yeah, the one thing is if nums L is less than nums R, right? What does this mean? This means कि if ever in one of those ranges they turn out to be just pretty much a sorted array, then it's pretty simple. We can always return nums L, right? This could always be the case. We could always return nums L, right? Like this makes sense, right? Right, if nums L is less than equal to nums R, this means that the array we're talking in is a sorted array in itself. So the first element, the element that L is pointing at, will be the shortest element. So this will work for all of the for all of these cases where the array we get is like this way. So 11, 13, 15, 17, 11 is less than 17, boom. Else, now we're talking about the case when the array is rotated, when array is not rotated. Now, when the array is rotated, how do we want to find the, so to speak, how do we would like to find the minimum element? So I guess let's look back into this. Let's do Control Z. Right. So again, if we are in a rotated array, we would, let's say we come to some middle element which is 5. I would guess we would want to like update our min pointer just in case every time we see this, right? So we are in the, I mean, the thing is, right, key whenever your array is rotated, because now in the else case we're only worrying about the rotated case, we know for a fact key the smallest element will be in our right sorted array. So our job should be to get our in a sense to get our attention to this sorted array. So I think the one thing would be for me to be like middle is equal to L plus R, record real quick, right? L plus R. And if I was going to check if nums L is greater than equal to nums middle, right? So if nums L, because that's the same thing we checked for over here, right? If nums L is less than, this means we are in the left sorted half, which is not something we want to be in. So what we will say is um, L is equal to middle plus 1, right? Exactly the same what we did over here. If we are in the, so yeah, if we are in the left sorted half, we would do middle because we want to be away from this, right? We are in the right sorted half, right? So this first thing we're going to do is min element do that. So we are in the right sorted half. So obviously this checks, and so now this is our L and this is our R. But yeah, technically this wouldn't run yet. Right? If this was running, then that would be great. But technically this would be 6 less than 2 does not still make sense. So we would check, are we, and so 0, 1, 2, 3, 4, 5. 5 plus 3, 8. 8 by 2 is 4. So we get 4. So now is 4 less than that. So this is our middle element, to be honest. Um, so is we on the right sorted off. What should we do, right? That's the thing. Now is the question of what the hell do we do now? One more thing he said interestingly was if we take in considering like a proper array, you will see it's increasing, right? But if you take 3, 4, 5, 6, 1, 2, you see it's increasing up to a point, and then this it decreases, right? This is the point where it's actually pivoting, and then it increases, right? So if we are able to find this transition point where you have increasing element and you have just a certain decreasing, then that could be very helpful for us, right? But how would we do that? um what does this mean? Like if this is not true, then this means nums L is greater than, okay, the yeah, so that initially means that, so whatever the L is pointing to, and now L is pointing over here and R is pointing over here, and this is our middle. So our L is greater than our middle. Hmm. be honest, I still don't understand this question. Like, I mean, I look at the video explanation, I'm still like, what does this question mean? So I guess we just have to look at the answer solution and try to figure it from that.
Okay, let's solve LeetCode 33 search and rotated sorted array. So we're basically given an array that was originally sorted like this one, but it became rotated. Also, time you're looking for a solution that's log n or better than linear, almost every time you're going to be looking for a binary search type solution. So since this array was originally rotated,
Wait a minute, wait a minute, wait a minute. Why am I looking at this? Sorry, chat. It's this quick. This is the question, right? I was like, what am I looking at? This not the um.
hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the and then take the minimum value and return it. To you that binary search might work in this case, but it's not going to be a traditional binary search. Now, of course, if
Wait a minute, pause. Let me just look at the discussions because that gives me a heads up of what I might be. Like I understood that part. Yeah, that's exactly, yeah. That makes sense. Find the largest element and then whatever ahead of
the
it.
entire array was rotated n times, that basically means we took a sorted array such as 1, 2, 3, 4, 5, rotated it n times, basically leaving it in the original sorted order. Now, if we had an array that was completely sorted like this one, an easy binary search would work on a sorted array, but if the array is fully sorted, then we know that the minimum value is going to be the leftmost, right? So if at any point we get binary search is going to run like this, a left pointer and a right pointer. If we ever get to a point where the entire array is sorted, we can just return the leftmost element, or at least consider this as being the minimum value. So let's try a binary search and see how it's going to be different than a regular binary.
I mean, this could be the case key this is equal, right? It could be the case that's equal. Could be. I mean, I don't know how, but for this is going to lead to like a time exceeded PS. There's no way, buddy. There is no way that this is passing in tests. There is no way. There has to be a time limit exceeded, TLEs, whatever they call it in the LeetCode lingo. Yeah, time limit exceeded. Knew it. The reason why is very simple. So
Search. Now, of course, we want to find the minimum value. We're going to initialize our left pointer here and our right pointer here. Basically, the current pointer situation means that we are considering this entire array to find the minimum. The minimum could be from anywhere in this array.
to be honest, nothing changes over here, right? We're in the right sorted half. To be honest, if we're in the right sorted half, I should do something like r is equal to middle minus 1 just to have fun. Because I want to like, if we're in the middle value, why don't we just like keep crossing paths and just keep going down, down, down? Like if we're over here, why don't we just like keep pulling it down, right? Oh, that makes sense. Yeah, again, I'm dumb. So let's just watch the video quietly.
And the result is going to be the minimum, and I'm going to keep track of that over here. Now, of course, one way we could do this problem is basically find the pivot, right? Find the position where, the elements are not in increasing order, right? From here to here, 3 to 4, they're in increasing order. From 4 to 5, they are in increasing order. From 1 to 2, they're also in increasing order. But from 5 to 1, they're in decreasing order. This is the pivot, right? So basically, this value is going to be the minimum. But I'm going to do it in a slightly different way where we don't necessarily have to, look exactly for the pivot. I'm going to take, left, right, take the half of them, get our middle pointer. Our middle is going to be over here at 5. So I'm going to consider as 5 being the minimum value we have seen so far, right? So our result is going to be 5. Now we have to ask ourselves, okay, this could have been the result, but now we don't want to, look at this value again. So the question becomes, are we going to search to the left or are we going to search to the right? Where are we going to find the minimum value? Where are we going to find a value that's even smaller than 5? Well, first consider this. since we rotated the array, we have two portions of the array that are sorted, right? We have this portion of the array that's sorted, the left portion, right? And we have the right sorted portion of the array, which is also sorted. So the question is for us, with this middle pointer, at this value 5, are we currently in the left sorted portion, or are we currently in the right sorted portion? Now, if we are in the left sorted portion of the array,
Then we know that there is a small element on the right sorted off.
we want to search the right sorted portion. Reason being,
We
if we rotated the array, the left portion is
always
always
gonna be
going to
big.
have values that are greater than
The
every value in the right sorted portion, right? Because when we rotate, right, suppose an array like
yeah.
this, we're taking the rightmost value, the largest value, and putting it over here, right? So we're taking larger values, putting them on the left side, right? So therefore the values on the right are going to be smaller now. So that's why it's always going to be that way. So if our middle pointer is currently in a value that's in the left sorted portion, then we want to search the right sorted portion because it has
Smaller
values in
values.
it, right?
Yes.
So how can we know if we are in the left sorted portion? Well, like I said, every value in the right sorted portion is going to be smaller than every value in the left sorted portion. So one thing we can check is if the current middle value is greater than or equal to
To
the value all the way at
on
the
the
left
okay.
of
Yeah,
our
so what he said was pretty much right, because if we are in the right sorted half, we know if we are in the left sorted half, my bad. If we are in the left sorted half, we know ki there are smaller elements. These elements in the left sorted half will be bigger than all the elements in the right sorted half. So we want to go to the right sorted half because we'll find the smallest elements, right? So thing is, if we are in the left sorted half, we would just want to push away from that. Okay, that makes sense.
our thing, right? Because the
Sure.
left value is going to be the smallest value. If the middle value is greater than or equal to the leftmost value, that means this middle value is a part of this left sorted portion, right? In which case we want to search to the right. Now, if our middle pointer, suppose in this case we can see 5 is greater than or equal to 3. The reason we're doing greater than or equal is technically this middle pointer could actually be
We
at the left position as well. That's one edge case. And in that case, we would also, this would be the left sorted portion. But suppose our middle pointer, instead of being at 5, was actually over here. It was at 1. What would our condition evaluate to then?
false.
Which is 3. It's not, right? Because the values
Yeah.
in this right sorted portion are going to be smaller than the left sorted portion, in which case this would evaluate to false, right? If it's false, that means, if we're at a value that's in the right sorted portion, then we want to search to the left, right? Because in this case, the right, if our middle was at this, it makes sense that, okay, all the values to the right of it are going to be greater. So then we want to search to the left. But obviously these values are also,
Wait, was it?
that means, if we're at a value that's in the right sorted portion, then we want to search to the left, right? Because in this case, the right, if our middle was at this, it makes sense that, okay, all the values to the right of it are going to be greater. So then we want to search to the left. But obviously these values are also greater, but that kind of doesn't illustrate the point, because what if our middle pointer was over here, right? Maybe we had some values over here. This is where our middle pointer is. We see 2. Okay, 2 could have been the minimum. Then we want to search to the left because we want to find even smaller values. Particularly, we would want to find this 1 that happens to be smaller, because we don't know where the pivot is. The pivot could be here, the pivot could be here, it could be anywhere. We just know we have to look to the left if we want to find smaller elements. If our middle pointer happens to be in the right sorted portion, then we want to search to the left. If our middle pointer is in the left sorted portion, then we want to search to the right. And I just showed you the condition we can use to detect that. So now I'm going to run through the example, and it'll probably make pointer was over here. In case if we ever got to our entire search, describing only works on a rotated sorted array. If we ever got to a point where let's say our right pointer was over here, meaning that, this is our entire search range, then we could not do this algorithm. In this
Yeah.
case, if we ever got to a portion of the array that's completely sorted, we would just take the leftmost value and see if it's smaller than our current result, and then
Yeah.
we would stop the entire binary search. Okay, so now let's run through the example. These are the conditions that I talked about that we're going to be using. So our middle pointer is here. Let's check so we checked that this might be the minimum. Now we're never going to look at this again. So now we're going to check, is this value greater than the value all the way to the left? Yes, it is. So we're going to search right. Since we're searching right, that means we're never going to search these values again, so we can cross them out. We're going to take our left pointer and shift it to mid plus 1. So our left pointer is now going to be over here. This is our new search range. And as you can see, this portion of the array is already in sorted order, right? How do we know that? Because the value at our right pointer is greater than the value at our left pointer. So that means that the array is entirely sorted, and then we can just take the leftmost value here, which is 1, see if it's smaller than our current result. Yes, it is. So then we can return 1 in this case. Now, just to kind of illustrate the opposite case, arbitrarily, I'm just going to say our middle pointer is actually going to be over here for some random reason. Let's just see how our binary search would work, which basically means we're searching left, set it to it's not. So we execute the else case, which basically we're going to take our right pointer, set it to mid minus 1, so our we shifted, take the leftmost value. So that's kind of, is this smaller than our current result? It's not. So our result, but I'm just going to left is going to be all the way our pointers are in a value. Every our result, but this sorted, not sorted mid. This mid value, we're going to put
Yeah, then we break it. Yeah, but I return it too, so it's the same thing.
actually update our results, setting the once we determine the portion, in which case we want to search the right sorted portion, so we can take our mid pointer, take our left pointer, and we're going to keep doing that until we find the solution or until our binary search has value.
Crazy. Why did this thing not work then? Hmm. I mean, he takes some minimum values over this. Why is it not passing though? Is it because of this? This can't be the case, right? That can't be the reason. Could be the case, you're right. Yeah, it could be the case that it's not technically because it's right, it could be that case. But I could do something like over here like this and it still work.
Concise.
Okay, let's try to understand what's happening. So if the array is not rotated, we essentially say whatever the min is, and the reason why we do this is because ये भी हो सकता है कि जो हम check कर रहे हैं उसका पहले min यहाँ पे आ सकता है, right? Could be the case where 3 4 5 1 2 and we somehow just come over here even though 1 is the smallest. Makes sense. Right, if we're in the left side half, then we know we want to check. these are my notes. So we just do middle, right? And if an so the logic is, if we in the left sorted half, we know कि इसके right में से भी छोटे बचे हैं, so we just do right. But wherever we are in the right sorted half, we know कि इससे आगे सब बड़े हो गए, इससे पीछे ही सबसे छोटे हो गए. So we do r minus middle this, and we return our result, so to speak. Okay, let's do this. So we have L is equal to 0, R is equal to length of nums, and we will say res is equal to num0, or you could say something like, and based on the constraints you can say something like 1001, right? This is a joke. Now you can say, well, let's this in any moment if our nums L is greater than equal to nums R, um, in any moment if the list we're checking is sorted, we will just say res is equal to min of res nums L, and because there's no use of checking more because we have reached that, else I mean we'll write middle, is equal middle is equal to L plus R, 2. Let's format the code real quick. Right, so middle is equal to L plus R divided by 2. I think that's how we did it. Yeah, and then I would do something very simple. We do res is equal to min of res middle nums middle, and we check if nums L is greater than equal to nums middle, then we will do L is equal to middle plus 1, else we will do R is equal to middle minus 1, return return result. What's the issue? uh what the, my bad. I was like, ये क्या हो रहा है? The second you see it pop, right? Yeah, anyhow, so the weather seems to be good, kinda. While this is, if it turns out to be sorted, I want to do more binary search question, to be honest. Like, I just want to put myself into that sure binary. So let me just see. Let's go to problems. Um, let's try to do some. This was what? This is, what does this mean? Okay, I just open the same thing. Okay, so rank transform of an array. Given an array of integers array, replace each element with its rank. The rank represents how large the element is. The rank has the following rules. Okay, so we are given an array of integers, which is called array, and we want to replace it with its rank, and the rank represents how large the element is. The rank has the following rules. The rank is an integer starting from 1. Okay, the larger the element, the larger the rank. If two elements are equal, the rank must be equal. Rank should be small as possible. Okay, cool. So we wanna do something like that. So we'll do this. Um, Again, it will be starting from 1. So I guess, okay, before we even code this, let's try to think of this. Return none, or return something like 1. Okay, so we are given, and this we're given 40 40, 10, 20, 30, and we want to return the rank, which is 4, 1, 2, 3. That's one example. We have another example. If we have 100, 100, 100, then we return 1, 1, 1. And we have another example where we have this, right, and we just return this. Okay, so it's somewhat like, if you can think of, yeah, so it's somewhat like if you were to traverse this, you would say this is smaller. Okay, like that, somewhat like that. We want to do this. How would we do it? And I mean, they have not given us a time constraint at the moment, but this is a binary search question. So I'm hoping they're like, this guy might mid-level. I would assume that they're wanting us to solve this in some way, but let's see. So I guess the one thing we would like to do is, I mean, is the array sorted? The array is not sorted. The array is not sorted. Yeah, so how can we do this in a way that's, I mean, the most simplest thing I can think of is that we sort this, and we get 10, 40, 20, 30. And then once we sort it, we pretty much give the index. So इसका index क्या होगा? इसका index होगा 0, 1, 2, 3. So it will be more like n log n plus n. So it will be an n log n solution if you think of. So my idea behind this is result is equal to, let's keep from 1 into length of array, and let's do array dot sort. Array dot sort. Um, we don't want to do array dot sort. Um, so I guess the simplest solution would be sorted array right? And this is our sorted array, so to speak. And this will be a result. So technically, how would you wanna do this? I think what we can do is, for I in range of length of res, what we wanna put inside res, you do increment by 1, right? So because right now this is our essentially, right now we have something like 1 comma 1 comma 1 comma 1, and this is what we have at the moment, right? So we want to give it in this order, and we want to give this, right? And once this is sorted, we'll have in this order, somewhat like that. So this is sorted. So yeah, if I sort this with 10, 20, 30, 40. And so how would I want to do this? So if I have a bunch of ones, I would like to res I should be equal to, so what should this be equal to? um I'm having hard time articulating my thoughts. 40, 10, 20, 30, and we have 10, 20, 30, 40, 1, 1, 1, 1. So if we are doing over here, we want to find the index, of the element by value in Python. So we're going to do list dot items dot index, something like that. So what we want to do over here is we would do sorted array dot index, right? We would do sorted array dot index of array of that I, and we would do +1, and this would then return res. Okay, so that passes. So yeah, this two passes. What's the issue? There has to be duplicates. So 37, 12, 9, 8, 5 plus 1 होना है उसमें. What's the issue here? So what could be the issue over here? What? Okay, this works over here. Um, it finds the first index if I'm correct. Yes. So is there any duplicates over here? Seems not to be the case. Why do we have 8? Wait a minute. Let me have something like the purpose. Let me have something like array is equal to this. Let me print out array dot sort. Something like this. Enumerate array dot sort. What's the issue? C I this, and we would then say what am I doing? What am I doing? 98. Okay, this should work. Let's see. See what's the issue. Okay. So 5 का 0 है, ठीक है. 5 is that. 8 is the issue of 18. What's the issue? 18 का क्या है? 7 है. I can't able to correlate what's happening. So okay. Okay. um मैं गलती कहाँ कर रहा हूँ? सो आउटपुट मैंने ये किया. This should have been. I'm so confused. What am I doing wrong? Okay, so for I in range of length of res. Um, 5 for 37. 37 का 5 है. Starting with 0, right? Yeah, one thing he also said is if two elements are equal. the there are no two elements that are equal over here, right? Oh, there are two elements equal over here. So this is 12, 12. समझ गया यार. I knew my mistake there only. Let's just print array dot sort. I want to see something. I think I understood what my mistake was. No, no, I mean, okay. Print sorted of array. That makes sense. So 12, 12 are equal. Yeah, so that's dumb. Um, there's an easier way to solve this set of array. Um, like, can't I do something like set of array? Right, set of array and then actually no, wait a minute. What do I do? This is sorted array and this takes a set. It converts it into a set essentially. And time limit exceeded. Wow, that's crazy. Um, yeah, so I think the issue is that now the algorithm is just not efficient enough, right? We were able to get an algorithm that works, but it's not efficient enough. So how do we decrease the speed of this algorithm? Right, so we have 40. Let's think of some like some binary. This has to be some binary search related something because I searched this topic. What I searched? Well, okay, topic is binary binary search. Okay, difficulty is language is what doesn't really matter. Status is what to do doesn't really matter. So how do we solve this in less amount of time, right? Let's think about this. Um, so we have 40, 10, 20. Um, how would I do this? So if you have 10, 20, 30, let's say this is the middle element. The thing is, right, this itself is taking some amount of time, but the majority time is getting into n log n plus n. So it's pretty much predominantly going n log n over here. N log n, to be honest, that's way too ahead of what we want to do. Um, how do we do this? And also, this is easy. So now I'm kind of solved it already, but it's not good time constraint. Also, the space complexity is a space complexity shit. Assuming that we're not considering the output, it's still of n and being the number of unique elements in that, which is not that cool. How do we solve this? I mean, you don't know how to do anything like that. Um, rank should be as small as possible. Rank should be starting from one, so you can't have like some rank going. This is one. This is 200, right? You have to keep it as small as possible. Um, how would we like to solve this? The thing is, right, the given array is not even sorted. So search in rotated sort array. Oh my god, guys, this I have to do this. With this I will do later, even though you guys may think I'm a rat for not doing that. But we have search. So we did search in rotated sorted array. We did search in rotated sorted array 1. That was we did. Now we have search in rotated array 2. What is this? There's an integer array, not necessarily with distinct values. यहाँ पे with distinct values. Okay. Before being passed into your function, okay, zero index. For example, my rotate at pivot index 5 and becomes this. So as you can see over here, um, it took, I guess, this elements and these elements and pretty much swiped them, right? And so yeah, given in the number array after rotation, the return target return, oh, is true or false. Okay. Okay, so yeah, okay, let's try to solve this. So I guess now that we know, this could be a good test of my understanding because now this space is on. So we have this array, right? So if we just look at this array, it goes something like 0, 1, so 0, 1, 2. Then it goes 4, 4, 4, 5, 5, 6, sorry, too much, 5, 6, 6, 7. So now we have duplicates, so to speak, right? And you can clearly see where the duplicates are over here. Duplicates are over here, duplicates are over here. Now we pivot this element. So we do the same thing as we did before. We pivot the element. This is our pivot. And so what that means is now, so now it starts somewhere over here. 6, 6, 7, and then we start 0, 1, 2, 4, 4. Okay, so now this is how our array is sorted, and now our question is to find that in, like, in that time. Okay, so how can we do this? So again, let's try to think about this as left half and left. Let's think about this as left sorted half and right sorted half. So again, over here we have two halves, right? We have our right sorted half, and we have our right sorted half and left sorted half, right? How do we ensure we can find that? So let's say, okay, so we can find middle over here, and we can check again with middle with this reference. Key, is this in the left sorted half? Let me just write some code. Um, okay, and just fluke of luck, if middle is equal to our target, we will turn true, right? So if this is else, I mean, to be honest, we can still say, like, over here this is 0, 1, 2, 4, 5, 6, 7, 8, 9. 9 by 2 is what? 4.5. So this is our, it's pretty much 4. So this is our middle element. Even now we can still say that if nums L is less than equal to nums middle, right? If it's still that the case, then we are in our left sorted half, right? We can still say that because I'm looking at the graph, and I can still say that we are still in the left sorted half, right? But can I say something like, okay, now that I know I'm in the left sorted half, let's say I wanna find I wanna find 4. I could technically find 4 here also. I don't understand. Oh yeah, it's not hunting. Okay, so now that I know over here, why can't I still just check if this is equal to the target, if the target is somewhere in the middle of this? Because if that's the case, I could still say r is equal to middle minus 1. And if it's not in that range, then I could always say, well, L is equal to middle plus 1. Why can't I say that? I'm so confused. Like, I could still say this, right? I mean, if it's not between 4 and 7 ka range. Um, why can't I still do this? I'm still confused. Like, am I gonna be extremely wrong? I'm not considering edge cases. I'm so confused because this would still work, right? Am I doing something wrong? Um, the thing is, this thing is actually not in the left sorted out. This is actually in the right sorted out part. But the reason why this is getting confused is because of this clause over here. If I were to change this as, let's say this, because now that wouldn't fail that test case. But I think that will lead to another issues because it's never that easy. So now again, so again, one is less than one, and that's not the case. So now we say, well, is it in within the target? No. So now it comes R, and now it comes L. Chat, man, oh man, this shit, bro. I'm not able to solve any question nowadays. Can we get an easy binary search question so I can feel good about myself? Okay, what is this? Search insert position. Given a sorted array of distinct integers and a target value, return the index the target is found. If not, return the index. Okay. Given a sorted array of distinct integers and a target value, return the index if the target is found. If not, return the index where it would be if it were inserted in order. So 1 3 4 5 0 1 2, great. 1 3 3 4 5, not there. So 1. Okay. Um, while um, middle is equal to L plus R, right? And so the first thing is we'll say, I think the first step would be to check if it's there, right? And I think I know what to do. It's actually easy. If you run binary search on this, right? If you run binary search on this, I'll show you. Let me just do 2 minutes. If nums target is, then return middle. Else what do we say? Else we say if nums middle was less than the target, right? So if nums middle, actually one thing I write is, if let's say we have the target and nums middle. So if the target is, let's say 3, right? In this case, like to be honest, like this is so dumb. We have one. Sorry, what am I saying? 1, 2, 3, 4, 5, 6, and we say 3. 3 is our middle, right? But let's say our 2. This is the case, right? Our target is less. So what we would like to do is we would say, well, is that the case? Because our target was less than that, so we're gonna search left side. So we're gonna say R is equal to middle minus 1, and else this could be the only one case, that is R is equal to middle plus 1. And over here this means target was greater than nums dot middle, so we're gonna check the right side. Else what we're gonna done. So this is interesting. Notch this. If we run binary search on this, will be 0 1. So let's say 1 3 5 6. If we run binary search on 0 1 2 3, right, and we actually just start the binary search, so 3 plus 0, 3 by 2 is equal to 1, so we come over here to 1, right, and we check. 3 by 2 is 1.5, so this is our middle. So our target is 2, so kya 2 is less than 3, right? 2 is less than 3, so we we're like, oh well, that kind of sucks. So we go L and we go R, and we say okay, we'll shift this to R over here. Now while L is greater than equal to R, so we do 1 0 plus 0, 0 by 0 is 0. If it's equal to target case 1, no, it's not equal to, but 1 is, so 2 is greater than 1, that means we're going to go ahead. So R, L goes ahead, R stays over there, right? But our middle value at the moment is 0 and we wanted 1. You see a pattern, like I don't know if you guys see the pattern, but I want to see if there's any pattern, right? Again, over here as well, if we were to do that, we have 0 1 2 3 1 7 is greater than 3, so we say okay, this is L and this is R, and we calculate 3 plus 2 5, 5 plus 2 is 2, so we check over here, right? 7 is greater than 5, so now L and R come over here, right? So now our middle value is 3 plus 3 6 6, how does that, 6 plus 2 is equal to 3, right? So we get that. So we get 3, right? And we check 3, and so we say 7 is greater than 6, right? And because we check 3, we push L ahead, as you see it's greater than that, so we push ahead L and R both here. Now we calculate 6 by 2 3, so 7 is greater than 6, so L pushes ahead. Now L goes ahead and this stops. So can you guys see one thing is, our middle value seems to have the answer, right? Our middle value seems to be always saying us whether it should be in the middle or not. Yeah, oh fuck, I'm just dumb. Sorry. um I know this answer. I can do this is easy. So this is 0 1 2 3, right? So once we run the loop, the first loop we run, like what does it say? L is less than equal to R, so L is less than equal to R. um okay. So 3 plus 0, 3 by 2 is equal to 1, so we check to 3, right? So middle is pretty much equal to 0 plus 3 is equal to 1, check 1, so 3, and this is looking for 3 is 2 is less than 3, right? So we come over here, right? So we come over here, L and R, right? And then we say 0 plus 0 is equal to 2, this is 0. Well, 1 is 2 is greater than this, so now our L comes ahead over here, and our R, so our R stays at 0 pretty much, and our L stays at 1, right? So in that case, it seems like L seems to have the answer because L is the one that shifts towards that side, right? Right. Um, let's take another example. So I know I'm working on a pattern at the moment. So again, over here as well, same thing. We'll have L is less than equal to R, and 0 1 2 3. So we say 1, right? And 7 is, let's say, greater. Let's 7 is greater than 3. So now L and R, 3 plus 2 is equal to 5, 5 by 2 is equal to 2, right? So 2 7 is greater than 5, so now LR over here, right? Both L and R over here, same thing. 6 by 2 is 3, 3 6 7 is greater than this, um, so we push L ahead. How does it pass for this though? We, it's wrong. It's the wrong answer. Oh, it's right. Okay, crazy. I don't know what I did. Why does this make sense to have L? the reason why I did this is because I saw the pattern. I don't know why, what was wrong over here. Um, 3 plus 2, 5, 5 by 2 is 2. So it checks, okay, 5, 7 is greater than this. So we check the right side. 7 is greater than 6. So we check the right side. So we check the right side. Now I actually don't understand the logic. What the hell? Yeah, I think, but the reason why I didn't, I actually,
Given a sorted array of distinct integers called nums and a target value, we have to return the index of the target in the we either find the target, or if the target doesn't exist in the array, then the two bounds will converge and eventually pass each other, meaning that the target was not found. With each iteration, we eliminate around half of the array. So now the question is, how many iterations does it take to converge on the target? Well, another way to think of it is, first we'll assume. Then we'll compare the element at index 2 to the target and figure out which one of the three scenarios we're in. It's either less than the target, greater than the target, or if neither of those are true, then it must be equal to the target. So the element at index 2 is 4, which is less than 7, so we know that the target has to be to the right of the midpoint. So we'll update L to be mid plus 1, so 3, since we know that the target is not at the midpoint and it must be to the right of it. Then we'll loop again. 3 plus 5 is 8, divided by 2 is 4, so mid is 4. The element at index 4 is 7, and we see that we found the target. That means we enter the else block and just return 4, the index of 7, and we're done. But what happens if the element doesn't exist in the array? Let's try this again, but this time we'll make the target 3. We'll start the same way by establishing the left and right bounds and calculating the mid index, which is 2. Then we compare 4 with the target, and we see that 4, first possibility.
no, because it's pretty much like a pattern thing that the way it's made, it's that. Crazy, crazy chat, crazy. I mean, I think I had fun. We learned a bit more. I have to practice, in a sense, sorted array and binary search because it doesn't seem that easy as it is. But yeah, I mean, that was fun. Wow, it's so dark, you guys can't even see me. Chalo, thank you so much for tuning in for another LeetCode / NeetCode grind session, and see you in the next one. Bye bye.